It's so big for one thing which is not in literature, I think it should be relaxed.
Hello everyone, welcome to today's Bangalore Theory Seminar. Today we have with us Sharat Ibrahimpur, who is a postdoctoral researcher at the Research Institute for Discrete Math in Bonn, Germany. Sharat obtained his master's and PhD in combinatorics and optimization from University of Waterloo in Canada, where he was advised by Dr. Chaitanya Swami. Sharat's research is primarily in designing approximation algorithms for combinatorial optimization problems, with recent focus on stochastic optimization and network design. Today, he will talk about his work on improved approximation algorithms for the flexible graph connectivity model. So let us welcome Sharat.
Yes. Thank you, Nashir, for the kind introduction. First of all, thank you, Arindam, for hosting me for this talk. It's a privilege to be here. During my undergrad days, back in 2011, I was spending my summer doing one of those summer research internships. And back then, I was more enthusiastic about cryptography. So, yeah, took my way to find my interest in combinatorial optimization. Right. So let's get started. Yeah, today I'll be presenting my recent work on the flexible graph connectivity problem. What I'll be presenting is an order log n approximation algorithm for this problem, and we'll do this by independent rounding. This is joint work with Laszlo Way, who is also at Bonn. Yeah, and this work will be appearing at IPCO this year. Let me just hit you with a problem statement, and then we'll get to the motivation right afterwards. So what is the flexible graph connectivity problem? In an instance of this problem, in an instance of P, QFGC, we are given an undirected graph G on a bunch of vertices and edges. We are given non-negative costs on the edges. I'll give you a partition of the edge set into two parts. Either the edges are safe or unsafe. A feature of the safe edges is that they never fail. Once you buy them, you can count on them to work. Unsafe edges might fail. I give you a connectivity parameter P, it's an integer, and a robustness parameter Q. What is the goal? To find a minimum cost of graph F. So you'll buy a subset of edges such that no matter which Q unsafe edges you delete, the remaining graph, the subgraph, so you bought F, J gets deleted. This remaining subgraph should be pH connected. Is the problem statement clear? Here I've drawn an instance, a graph, green edges are safe, dashed red edges are unsafe. And the costs are shown next to the edges. Here P equal to 1 and Q is also 1. So what this means is I just want the vanilla connectivity against one edge failure. Okay? And I've shown two solutions there. You can either pick a cycle on the unsafe edges. No matter which edge fails, you still have connectivity. Or you can pick two safe edges. Is the solution on the right has a lower cost. Is that the optimal solution for this instance? Yes, exactly. That's right. So if you do that, you don't have to necessarily stick to unsafe edges. You can also purchase a cheaper safe edge. It always makes sense to pick a safe edge, right? If there are parallel edges. Right. And one quick remark, in all the problems we'll discuss today, we will pick at most one copy of each edge. Yeah. If there are parallel edges, you can pick at most one copy of each of them. Is someone accepting? Okay. So how can we characterize PQFGC solutions? Here's a very simple cut characterization. And then set F is feasible for the problem if and only if. Look at all cuts in the graph. Take a non-trivial subset of vertices, take its complement, contract these two vertices. You just get a two vertex graph like this, and there are a bunch of edges going in between them. This set should either have P safe edges or P plus Q total edges. Does that make sense? If you have P safe edges, you know at least this cut is safe. And if you have P plus Q edges, no matter which Q edges fail, you're good. You'll be left with P edges. So, and if this happens for every cut, then you can be assured that the solution is PQFGC. Observe that PQFGC nicely interpolates between pH connectivity and P plus QH connectivity. If all the edges are safe, then you get pH connectivity problem. All edges are unsafe, you get P plus QH. And this problem sits somewhere in between, depending on the instance. Yes, let's just do a mini quiz. Is this graph 2, 2 FGC feasible? So you want two connectivity and you want to be robust against two edge failures. And just a quick note, these are the green edges, these are the red edges. What? This is the solution. The solution, if I purchase this, am I 2, 2 FGC feasible? Who thinks yes? Okay. Who thinks no? It is in fact feasible because this gives the safe cycle gives you two connectivity. You don't have to worry about any number of failures. And you have four edges connecting here. No matter which two fail, you're still getting connected to connectivity to a two edge connected. So you have 2, 2 edges. Right. So pH connectivity means between any two vertices, you want there to be P edge connected, edge disjoint paths. So connectivity means just having a path, two edge connectivity means two edge disjoint paths. So you should be able to send, like, think of it as like sending in the undirected graph, you should be able to send P units of flow along these. Yeah, that's the idea. Please, and feel free to interrupt me if you have any questions. I do want to make sure that the concepts are clear.
It's also incorrect definition, right? If P minus one edges are deleted, then
Exactly. A graph is P minus one edge connected. If no matter which P minus one edges you delete, you still have connectivity between any two words. And here, this is taking a bit further than that. It's saying, okay, you can delete P minus one safe edges, or like you can delete, yeah, think of it as you can delete any P minus one edges, and on top of that, you can delete Q unsafe edges. That's how, and you want like connectivity in there. That's what is happening. Yeah. Any other questions? So what's the motivation for studying this problem? This problem was introduced by Adjiashvili, Hommelsheim and Mühlenthaler in IPCO 2020. And they wanted to like come up with a model for survivable network design problems, where edges have like a different failure model. They wanted like a non-uniform model. And that's where like they came up with this motivation. Imagine like you have a road network, you own this road network and you have like already have some connectivity, and you're also renting some edges from another party. But you don't rely on them to provide like service at all times. They might have some failures, right? And you still want like some guaranteed service, the pH connectivity guaranteed. So that's the motivation for studying this problem. And they mostly investigated the 1,1 setting, the most basic setting when there's at least one failure and you want connectivity. And observe that this model, the simplest model, already contains many prominent problems, right? the minimum spanning tree problem. If the instance has only safe edges, we get the minimum spanning tree problem. If all edges are unsafe, we get the two edge connected spanning subgraph problem. Tree augmentation problem. Imagine your instance only has unsafe edges and there's a tree of cost 0, a spanning tree. And now you want to augment it to a two edge connected subgraph, and also forest augmentation problem. So many very hard, like fundamental problems are a special case of this problem. Let me quickly mention like what is known about, what are the results known in this model. So since the introduction of this problem, a lot of work has happened. Like there have been a series of papers. I'll just quickly describe like what is known, and then I'll mention what we did in this work. So the Q equal to, so the columns are for the connectivity parameter, the rows are for the robustness parameter. When no failures can happen, this is the classical problem of pH connectivity. When P is 1, we can solve the problem optimally. That's a spanning tree. P equal to 2 and general P, you can use Fuller and Wishkin's result. It's a 2 approximation for obtaining a minimum cost pH connected subgraph. So let's look at the non-trivial cases basically in this model where failures can start happening. Adjiashvili et al., what they gave was a 2.523 approximation for 1,1. It's a connectivity against one failure, one unsafe failure. When we, like with other co-authors, with Sylvia Boyd, Joseph Cherian, and Arash Hadadan, we had a result where we got down this factor to 2. So it matches the known result for the 2H connectivity problem, because 1,1 FGC already includes the 2H connectivity. So we match that result. We also showed that there's a 4 approximation for general connectivity against one failure. And then we showed that there's a Q plus 1 approximation. If you just want connectivity against Q failures, then you get a Q plus 1 approximation. And then for the most general case, we had given a Q log n approximation. So this was back in 2020. Subsequently, there were 2 sets of work. Again, this work is with Ishan Bansal, Joseph Cherian, and Logan Kraut. Here, what we showed was for with 2 failures, we gave a 6 approximation for even connectivity case and 20 for odd connectivity. Basically, like we were stuck, we didn't know how to make progress, so we started working with small values of P. And simultaneously, in the same ICAL at the same ICAL conference, Chandra Chakuri and Riya Jain also had like some results on this problem. They showed like an order P approximation algorithm for up to 2, 3, and 4 failures. They also obtained some results for the small P, Q case. They also obtained a result 2Q plus 2 approximation when there can be an arbitrary number of failures, Q failures, and 2 correct. Nutov improved the analysis to a 7 approximation in that cell. Recently, Ishan Bansal obtained a 12 approximation for P, 3, and yeah, here comes the more like some recent exciting progress. What Ishan Bansal, Joseph Cherian, Sanjeev Khanna, and Miles Simmons, what they showed is that for vanilla connectivity against Q failures, they removed the dependence on Q. They obtained a constant factor approximation. And this is what inspired our work. The techniques in this work form a starting point in the result I present today. So that's the 7 approximation. And in this work, we'll give a order log n approximation for the general case. So there is no, so for the longest time, we were wondering like what happens for the general case. We were mostly working with assumption that P of Q is small. Here we handle the general case. Any questions? And all of these like techniques, like they mostly involve like you find a P, Q of GC solution, and if you want to handle one more failure, then you try to make the network more robust, and then that's how you lose like the approximation factor. You start with a two approximate solution, you spend another 2 times opt to obtain robustness against one edge. So that's how those results were obtained. I won't get into the details.
So what is happening in the last row, 7 and log n in between? Is there something better known for p equals to 2, for example?
No, currently no. But that dependence on n is also not that nice, because while p and q might be constant, like the graph size just keeps growing. So yeah, it's still, there's a lot to be understood about this problem. The two is like because it includes the two-edge connectivity problem, there hasn't been any progress on that problem. It's one of the fundamental problems in combinatorial optimization, where a better than two approximation is not known for the general cost case. So we yes, the problem is also APX hard. There's something like 1.06 APX hardness or something, or maybe even smaller, 1.02. All of these are APX hard problems. You don't expect a p-dash. But for PQFGC, we don't know anything like better than like than the hardness result known for the classical cases when there are no failures. So not much is known about this. So there's also like some related work where you consider the unweighted version. All edges have uniform cost. There were some results known before, and there have been some improvements in that end. I won't again get into these ones. There has been like some work on the unweighted version. There's some work on like a related model called flexible vertex connectivity. Now vertices are either safe or unsafe. Then a few unsafe vertices might fit. And there have been like other like extensions that have been studied by Cheturi and Jain. I won't get into these details. Let's see what we'll be doing in what we'll be seeing in today's talk. So there's 3 parts. In the first part, I'll talk about the heart of our work. It depends on coming up with a new linear characterization of the feasible solutions, of the integer feasible solutions. So prior to our work, such a nice LP was not known for P, Q, FGC. There were some formulations, but they were like quite big, or like you couldn't design the separation oracle. And here the main idea is that you use knapsack inequalities. And I'll get to the details shortly. Second part is about designing a separation oracle. This was the challenge for prior LP formulations. Here, there's a very nice way of solving the LP. And then the third part will be just like an independent rounding of the LP solution. The algorithm is extremely simple. You just take the LP solution, you scale up this vector and use these as probabilities to sample edges. You just build a random inside and use Karger's bound on the number of near minimum cuts. Use Chernoff tail bounds, concentration inequalities. Then you apply very vanilla union bound argument to show that your feasible solution is the random solution you obtain is feasible with say 50% probability. That's the strategy we develop. Okay. So what are the valid inequalities that we have? So recall the characterization. On every cut, we want to either pick P safe edges or P plus Q edges. You can pick more, then no one's stopping you, but at least P safe edges or P plus Q edges. When you see those numbers, what is one very easy way? Like if any of you have played around with like edge capacities and capacitated network design, the very natural choice would be to do this. For safe edges, give a capacity of P plus Q. For unsafe edges, give a capacity of P. And say that your graph should be P times P plus Q edge connected, like in a capacitated sense. You can write such a problem. Again, that's also an NP-hard problem. But at least from a modeling point of view, you can start. That could be your starting point. So you can write a valid inequality like this in your LP saying, with respect to these capacities, this variable is a Boolean variable in your integer program, which says whether the edge should be included in the solution or not. You're saying on every cut, you want to, in total, pick a capacity of P times P plus Q. Okay. Let's say you write this.
Could you explain what P times P plus Q?
Because if you pick P safe edges, then P times P plus Q will give you this. If you have P plus Q total edges, then each one has at least capacity P. So this is like a very crude inequality. This is a valid inequality. You can write this. Feasible solutions will pass this test. Okay, so take two extreme solutions. If your solution had exactly P plus Q unsafe edges in effect, you would pass this test. If your solution had P safe edges, again, you would pass this test. You're at least not cutting off feasible solutions by writing this. Okay. Is this sufficient? Would we be done just by writing these inequalities? What do you, anyone? Yes? Is sufficient? Okay, so we'll see. So look at when you write a capacity constraint like this, it's a linear constraint. Because the capacities are P plus Q and P, I could trade a safe edge for 1 plus Q over P unsafe edges. The capacity won't change if I do this trade. Assume that Q or P is an integer. Let's not worry about all this, our corner cases. Okay. I can do this trade, the capacity constraint will still hold, but this makes the solution infeasible. Right? For instance, take a solution. It has one safe exactly, one safe edge, and those many. You started with P plus Q unsafe edges. You traded 1 plus Q or P unsafe edges for one safe edge. Again, verify the inequality, it will pass. But we know this, neither of these solutions is feasible. Right? Because this neither has P safe edges, nor it has total, like the total number of edges is just P plus Q minus Q or P. So the solution is infeasible. So that valid inequality, it's a valid inequality. It does not cut off feasible solutions, but it also leaves behind some infeasible solutions. So that's what is happening. And the F2 prime is another way. You started with P safe edges and you traded, you left one unsafe edge, one safe edge and bought 1 plus Q or P unsafe edge. So how can we remedy this? Like, because we were writing like this very simple capacity constraint and then we are hoping this works, but it doesn't work. We could have ended this and gone for snacks, but unfortunately not. We have to do some more work. So this is where like knapsack cover inequalities come in. So the idea of cover inequalities is that if you have found a partial solution, the remaining residual solution has to do, I guess it comes like there is something called cover inequalities that are used for like strengthening LP formulations when they are too weak. Knapsack cover inequalities, the reason I added the prefix knapsack cover inequalities is because like it was this very popular work, famous paper where for the knapsack problem, like these constraints were added and the unbounded integrality gap example was brought down to once. So that's like, so let me explain the idea with a concrete example. So on the previous slide, we saw an infeasible solution. It had one safe edge and a bunch of unsafe edges. Observe that our goal is to detect infeasibility in this. Here's the trick. Let's say I've already purchased this one safe edge. From the entire edge set, the cut characterization says either you should have P safe edges or P plus Q total edges. But let's say I told you, okay, I'm giving you one safe edge for free. Now I ask you this question again. What is the residual requirement from the remaining solution? It's no longer P and P plus Q. You'll be like, okay, I already have a safe edge. The residual requirement is either I have P minus one safe edges or P plus Q minus one total edges. And now the numbers are different. You have edges. Now let's give the residual capacitors. Previously we gave P plus Q and P. Now we'll give P plus Q minus one and P minus one. Now we'll ask this remaining, the cut on this other solution, the other than what we purchased, should satisfy this, like same way the capacity constraint was written. So let's write the same thing. Let's look at the U prime capacity of this edge set, the edge set without the safe edge on this cut. You no longer have any safe edge because you've already like purchased it. So it's P plus Q minus one times zero. And then you have a capacity of P minus one on these remaining unsafe edges. If you do this calculation, observe that it's strictly less than, this term vanishes. Strictly less than P minus one times there's this negative term. So it's strictly less than this. So you can detect that this is an infeasible solution just by imposing this capacity constraint. So that's the idea behind knapsack or inequalities. If you've already purchased some solutions, adjust your residual requirement, then ask the remaining solution to do more work or for attaining feasibility. And you can also detect the infeasibility of the other solution F2 prime in the same way. I'll write the inequalities again. I'll show it properly on the next slide. Because is imagine P and Q are large, like for now. Even if, yeah, I think this is still a negative term. Yeah. If P is one, then it won't. Yeah. Any other questions?
So this has to be generalized for multiple edges.
Exactly. That is what we'll see on the next slide. Okay. It's very easy to extend this idea. So this is what we'll do. So this is the key lemma. Yeah.
Right now we actually we had this constraint that said if we have a desirable cut, then that inequality will be cut, right? Now you are trying to include more constraints which say that which kind of like guarantee the reverse.
Yes, that is correct. Because some solutions were cheating the inequality. You are like, oh, they're cheating because they are doing these trades. And we're like, okay, I've detected that you have made these trades. Now I give you a new inequality to satisfy. Your feasible solutions will keep satisfying these, whereas infeasible solutions have to do more work. And this is the main key lemma in our work. That guides the entire algorithm, like everything is built on this. What do we say? And edge set F is feasible if and only if, look at any cut R. Look at all partitions. Look at the edges on this cut, the F edges on this cut, split it into two parts, J and K. J is the edges you have already bought. K is what you want the LP to tell you how much to buy. In J, let's say you have bought a bunch of safe edges, which means the safe requirement goes down by how many ever edges you have bought. Okay. This plus just means you cap it down. Okay. You don't let it become negative. Okay. And here the term is the number of unsafe edges that you still need. Okay. So what is this saying? If you've already bought like J intersect S safe many safe edges, then your residual capacity has gone down. So safe edges now. So observe that K is the edges that are not in J. So the safe edges in K, their coefficient will be this term plus this term, whereas unsafe edges only have this coefficient. That's exactly. So the residual capacities are Safe edges get this green term plus the red term capacity. Unsafe edges just get this one. And the right hand side is just the product of this times some just some math you can see if you stare at it long enough why this is the right expression. And basically, like this example on the previous slide, you can do it in a more general way. Okay? And the nice thing is this is the exact characterization of integer feasible solutions. So I leave the proof as an exercise. We won't get into the details. But let's quickly see, does anyone see why infeasible solutions won't pass this test? Does anyone see a quick certificate? Let's say F is infeasible. What does infeasibility mean? That is some cut where you have strictly less than P safe edges and strictly less than P plus Q total edges. What should you take J and K as? Close enough. You can actually take J to be exactly all the edges on the cut, both all the safe and unsafe. Okay, what happens? Let's say, because you know J has strictly less than P safe edges, this term is positive, at least one. It has total edges less than P plus Q. Again, this term is positive. Okay, so the right hand side is positive. Now, what about K? That's just an empty set because you picked everything in the intersection of the cut and the F edges. Right, so this term, left hand side is just zero. So you've just killed the infeasible solution. By the way. Any questions? Okay. All right, so this is the characterization. This tells us a very natural linear program for the problem. What do? We just linearize these capacity constraints plus knapsack Fermi inequalities. Let's write a linear program, minimize C transpose X. The cost of edges you have picked, subject to now this complicated looking constraint, which is just a linearization of what we did before. For all cuts R and all possible conditions, J is what we have already purchased. K is what we want the LP to guide us to make a decision. So if I've bought a bunch of safe edges, I decrease this coefficient by a corresponding amount. And same for this. And the right hand side is also adjusted. X of K is telling us how many K edges to purchase. And this is telling how many safe edges in K to purchase. That's the help. Observe that because this should hold for all cuts and all partitions, it should in particular hold for the partition when J is the empty set and K is the rest of the cut. So what this means is this one, because this term is zero and this term is zero, you just get P times X of K plus Q times X of K intersect S is at least P times P plus Q. That's the vanilla capacity constraint where you had the capacity of P plus Q on safe edges and P on unsafe edges. So you still have that and you add it like some more. Why is this LP formulation useful? In the next like 5 to 10 minutes, we'll see why we can efficiently separate over this so that we can actually solve this LP. So what's the main idea for separating over this LP? So what is the task at hand? I give you a fractional solution where each edge has some value between 0 and 1. And you either tell me that, okay, X is a feasible solution, or you tell me which LP inequality the solution does not satisfy. So I need to recognize such a violated inequality. I need to recognize a cut and also partition J union K. And this is the inequality that I want to establish, a strict inequality instead of a greater than or equal to, it's a less than. So we can easily check the case when J is the empty set and K is all the edges on the cut. Why is this easy? We can just set the following capacities, edge capacities. I'm given the fractional solution, it's a fixed choice. On safe edges, I'll install a capacity of P plus Q times XC. On unsafe edges, I'll install a capacity of P times XC. By doing this, now I can use just use any of the flow algorithms for finding a min cut. Just see if there is a global min cut whose capacity is strictly less than p times p plus p. If yes, then you've already found a violated inequality. On the other hand, let's go to the other extreme. Let's say the min cut is already large, is at least in this auxiliary graph, like the min cut is at least p times p. Let's go to the other extreme. Let's say there is a cut such that its capacity with respect to these capacities is at least 2 times p plus 2p times p plus q. My claim is that there can be no violated inequalities that can arise from such a cut. No matter which J union K you choose, there cannot be a violated inequality. The reason for this is, if I tell you that this linear expression, this left-hand side is at least 2p times p plus q, I know that either this term is at least p, one of them is at least the average, or the other term is at least p plus q. Now it doesn't matter which J you choose. It's again, you can do some elementary math and show that you cannot have a violated inequality. The only cuts now we need to worry about have a capacity between p times p plus q and 2p times p plus q. And because the min cut is already this value, so all these cuts are 2 approximate minimum cuts. And this is where like David Karger's result is useful to us. What we know is that the number of 2 approximate min cuts is at most n to the 4. It's polynomial and the size of it. And we can efficiently enumerate over it. Now let's say I can efficiently enumerate over these. I need to test whether each of these cuts are safe. Like, are there any violated inequalities? I want to test this. Okay. Now observe that there's only so many choices of J intersect safe edges and J intersect unsafe edges. At most p times p plus q. So first of all, assume there is a violated inequality. It has some number of safe edges, a many, and there's some number of unsafe edges, b many. You're going to guess this. There's at most polynomial many choices. Now my task of finding a violated inequality just boils down to checking this. P minus a plus q minus b, positive portion, blah, blah, blah. I can write this. I want to find such a violated inequality. And now that I've already fixed how many safe edges I should pick and how many unsafe edges I should pick, let's stay at the left-hand side. This is just saying I'm summing the x values on the safe edges in K. This is summing the x value on the edges that are unsafe and in K. And I want to establish that this is strictly less than some quantity. This is a fixed constant now. I've fixed all the parameters. Want to make this left-hand side as small as possible. That's a very natural choice. You just make a greedy choice because you've already constrained this and you want to make left-hand side small. So what you do is in J, you include A safe edges with the largest x value. And you'll include B unsafe edges with the largest x value. So that way you're hurting K the most. And by doing this, you have made this left-hand side as small as possible. And now you will check the inequality for this choice. If there is a violation, you're happy, you'll report that. If not, you know that at least this cut is safe. And you do this for all the n to the 4 cuts. And that's your separation. I'm sorry, this might have gotten a bit technical, but if there are any questions, I'm happy to answer. Okay. If not, let's now quickly, I'll spend the next 5 minutes just on the algorithm, and maybe if you have a few minutes on the analysis. Let's see. So what's our algorithm? Solve the LP using ellipsoid method and find an optimal or a near optimal LP solution. Let's call it X. I'll define the vector Y as just, I'll scale up the solution. I'll scale up by log n. That's where the log n shows up in the approximation guarantee. I'll scale up by 100 times log n. And if any of the numbers exceed 1, then I'll just cap them in. That's the vector 1. And the solution that I output now will just be this random edge set f. I do an independent random. Each edge I'll pick with probability 1 independently. And that's my solution. The theorem, the claim is that this solution is feasible and has bounded cost, order log n cost, with respect to the LP solution, LP cost, with constant probability. That's it. So this is easy to see because the probability that you pick an edge is simply scaled up by this. So the expected cost of your solution is 100 times log n times the LP cost. By Markov's inequality, half of the times it should be at most this number. So I'll ensure that that happens. The remaining 1/6 probability I use to ensure that it's also feasible. Now I want to argue that this F is not infeasible too many times. It cannot happen too often. And this we do by a union bound over all the cuts in the graph. And this is where again we use Karger's result. The number of small cuts, like alpha approximate min cuts, the min cut is at some value lambda. The number of cuts with value at most lambda times alpha is at most n to the 2. So it's some polynomial bound, which depends on where the exponent depends on the approximation ratio to min cut. Here the approximation is with respect to the capacities. This is unrelated to the costs that show up in the PQ of GC problem. And we do the failure probability analysis for a single cut using a Chernoff lower tail bound. And we'll say that, okay, on this cut, the probability that we pick too few safe or unsafe edges is very rare. It happens with very small probability. And then we'll do a linear bound. That's the strategy. I don't know how to de-randomize this. I think Karger's result has been de-randomized. There's Nagamuchi et al. Paper where they show how to enumerate overall alpha approximate min cuts. But this particular algorithm, I don't like. Basically, if you want to test feasibility, like wherever you're using Karger's bound, if you have a specific graph, you're interested in some near min cuts, that you can do deterministically. But we don't know how to ensure PQFGC feasibility. That's a good question, but yeah, we haven't thought much about de-randomizing this. But in general, for this technique, there are more basic problems where it's not known how to de-randomize. But this kind of strategy of scaling up the LP values and using them as probabilities is a standard tool. Okay. Let me show a quick slide on Chernoff bounds. So first of all, like remember that recall that we are including an edge in our solution, random solution F with probability little value. There are some edges which might have already hit the cap of 1. These edges will always be there. F naught is exactly the same. For the remaining variables, I consider this random variable capital Y, which just says whether this edge was included in the solution or not. Okay. And this random variable has expectation little y. What we know from Chernoff lower tail bound is that for any subset K of edges, the probability, so take a subset of edges, there is some expected value of the number of edges you pick from this set. Let's call that mu, say. And the probability that you pick less than 99% of mu, many edges, is very small. That's what it says. There's very strong concentration around the mean. And a convenient bound here says if your mean is like 100 times log n times some number, the probability that you pick less than 33 times log n times that number will be very small. It will be like e to the negative 100 times log n over 5. So that's like 20 log n. So you get like an inverse polynomial bound by units. That's why the log n was introduced. And it's a way to make the analysis go through. I still have 5 more minutes. Okay, yeah. So this is the last slide, and then we'll just look at some open problems. So let's see the analysis for a single cut. So let's consider this capacitated auxiliary graph. What I'll do is, again, the same trick as before. I'll give safe edges a capacity of p plus q times the LP value. There's the fractional LP solution we have, which was used for rounding. And for unsafe edges, we give a capacity of p times x. My LP feasibility already ensured that the min cut is quite large. It's at least p times p plus q in this auxiliary graph. Now take some cut. I just want to analyze that f is this random set is not infeasible on this cut. That is, and I'll do this separately for each of the 2 to the n cuts in the graph. Take some any partition, like the LP constraints already impose something, right? Like we wrote this LP with like all possible partitions of the X set into J and K. The LP said this particular linear expression should be at least this right hand side. So I know the X values on K cannot be too small because they impose that it be at least something. Can anyone think of a very natural choice for J? Like I have fixed a cut. I know my LP constraints ensure this for all possible partitions. The idea behind knapsack or inequalities was something. It's like if I've already purchased something, then I need to adjust my residual requirement, right? What are the edges I've already purchased in this case, in this independent rounding thing? F is the random set. There was one which was always big, F naught. So that's the interpretation of the LP. If I've already purchased something, the other should work hard. I know F naught is already purchased. So let's see. Yeah, J is exactly like, yeah, that are intersect F naught. So now define little a to be the number of safe edges here and b to be the number of unsafe. So if I've already picked at least p safe edges or p plus q total edges, I'm done. 100% done on this part. The edges that are always picked gave me feasibility. Yeah. Otherwise, again, I can rewrite this in this particular way. Some linear inequality with some complicated looking terms. But the idea is that the x value on the k edges is sufficiently large. That is what this inequality is. Yeah. Here, yeah, you get this inequality, and basically, like these are some these. Yeah, you basically like say that, oh, the LP is already telling me this inequality holds. Because my solution y was a scaled up version of x. And recall that all the edges that go into k, they were so small that even after scaling up, they didn't hit 1. Because the ones that hit 1, they went into j. So I can just scale up this inequality, and I get do a change of variable from x to y. And my right hand side is very large now. It has a log n term. And now you can argue that either, again, one of these two terms is larger than the average. So one of the terms is sufficiently large. Either in expectation, you're picking a lot of safe edges, or in expectation, you're picking a lot of unsafe edges. That's what you get. And what I mean by a lot of safe edges, you're picking at least p minus a, that was the residual safe edge requirement, multiplied by 50 times log n. So again, you apply Chernoff and you say that, oh, the probability that you pick strictly less than p minus a safe edges is very small. It's less than n to the minus 10, a very small quantity. And in either case, you get this. And for more general case, if you started with like your cut having a very large capacity, not just at least p times p plus q, if it was larger than 10 times p plus q, then you'll get a much smaller failure probability. This is all like standard stuff that people do when they are doing unique bound cuts. I don't have to walk through the calculations again, but that's the idea. And then
Why is the constant so big? Like why generally in these arguments it would be like 10 or something.
we didn't try to optimize the constant. I'm sure like you can shave off like another few small factors, but you cannot say, for instance, at least for this technique, you cannot go from log n to log n or log log because you're applying the lower tail bound. If you're applying the upper tail bound, then if you are trying to control the congestion or something, then you could have shown something like log n over log n. But for the lower tail, usually you need log n and some constant. And because you're anyway losing log n's, you don't try to optimize the constants too much. A more interesting question would be like, how do you do the analysis so that like you lose a much smaller factor in approximation? Let me conclude this talk now. What we saw in this talk is a new integer linear program for PQFGC, which was obtained by writing knapsack inequalities on top of the vanilla capacity constraints. This gave us an exact characterization of PQFGC solutions. And the nice feature of this NP was that you can efficiently separate it. You can actually solve this NP. And then you can do, and then the algorithm was just an independent randomized random of the LB solution, a scaled version of the LB solution. And this gave us an order log approximation. Something is, I guess I can just go to the next slide here. So let me just leave you all with a few open questions. What is the integrality gap of this LP? We showed an order log n upper bound, but what is the true answer? Can we somehow remove the dependence on the size of the graph? Maybe it is just a function of P and Q, or maybe it has no dependence on P and Q. It's a constant or something. And are there any lower bounds on the integrality gap of our LP? Can you show that? And then also, can we obtain order one approximations when P or Q are small by starting with this LP? With this, I'll conclude my talk. Yeah. Yes. It still has exponentially many constraints because all the cuts are there and yes, yeah. So it looks like there are a lot of constraints, but the nice feature of this LP is that you can still separate over it.
You assume that P and Q are constraints.
They can also be part of like, no, not really needed because they're at most n. Assume they're at most n. And then P times P plus Q is still polynomial. All of that is. No, still like all the results are from the classical results where Q is 0. There is like an NP, very standard NP that has an integrality gap of 2, the cut LP for, yeah. Yes, yeah, but that would apply because this problem is more general, but it would be nice to obtain something even stronger than that. Right? Yes, yeah.
So we have a big one.
2,0. Yes. Any other questions?
Thank the speaker.
Thank you very much.
We have snacks outside.